Naming ionic compounds. Naming of ionic compounds is it can be a bit confusing. Largely it's because naming compounds is historical. And so the first thing we have to realize is that we have to know if it's an ionic compound. An ionic compound is a metal with a nonmetal, or some sort of polyatomic ion. Polyatomic ion being a covalently bonded molecule with a net charge. And so we have to be able to name these things, and there's several different situations. So the first one we're going to look at is where we have a metal with a nonmetal. We have sodium and we have chlorine. Sodium is over on the far left right where all the metals are, far left hand side where all the metals are, and chlorine is on the upper right hand side where the nonmetals are. And so we have sodium and we have chlorine. Now, if it's just the atom, and what I mean by just atom is not how many you have, but it's just the atom. Then what you do is you take the ending and you chop off the ending of the nonmetal and you replace it with "ide." So this becomes not chlorine anymore, but chloride. IDE. And so we have chloride. And so the way we name these ionic compounds, particularly if we just have just the atom, is we say the metal, which is sodium, and then we say the nonmetal part, and we chop off the end and replace it with "ide," so it becomes chloride. So this is sodium chloride. And you probably have said this before, without even realizing it. Sodium chloride is, well, that's the way you actually say the name of that compound. So we can take a look at something else. Let's take a look at, say, calcium bromide. So we say the name of the metal, just say it, it's calcium. And then we take the name of the nonmetal, which is bromine, and we chop off the end and replace it with "ide," bromide. So this is calcium bromide. Now, I'll caution you here. Ignore the fact that you have a 2 there. The 2 bromines are for charge balance to go with the calcium. But the fact that there's 2 of them there doesn't matter as far as the name goes. So what you don't want to do is say something like calcium dibromide. Okay, your dis, tris, tetras, pentas, hexas, those go with what are called covalent compounds. More on that later, but this is just calcium bromide. Chop off the end, bromine becomes an "ide," and fluorine becomes fluoride, and so forth, and oxygen becomes oxide. So let's take a look at another one. How about we do this compound here, and how would we handle that? Well, first off, aluminum is a metal, and oxygen is a nonmetal. So that means this is ionic, and you have to ask yourself that every time. What do I have? Do I have an ionic compound, which is a metal with a nonmetal, or a polyatomic ion? Or do I have a covalent compound, which is a nonmetal with a nonmetal? Well, aluminum's a metal, oxygen is a nonmetal. And so we would name the metal aluminum, and then we take the ending, that is oxygen, and that becomes oxide. And there you go. We have aluminum oxide. Aluminum oxide. So you have to look at it and decide, do I have a metal with a nonmetal, or do I have a polyatomic ion? And so if it's just the atom, and when I say just the atom that's attached to it, the non-metal, whether it's 1, 2, 3, or 4, it doesn't matter. What matters is it's just an atom. We say "ide." So this becomes oxide. Now, if we have something that has more than one possible charge, on the other hand, we have to be very careful. And so we have these two compounds here. Both of these are iron oxides. We have iron with 1 oxygen, and then we have 2 irons with 3 oxygens. And both of these are iron oxides. But we have to be able to say, well, which one is it? And it goes back to the charge. As previously explained, you can figure out the charge based on what you know to figure out what you don't know. And I know that oxygen is 2 minus. Therefore, to get the irons to add up to 0, that iron has to be a 2 plus. And so we have to specify what kind of iron it is. This is an iron with a 2 plus charge. So what we'll say is we'll say what the charge is on that iron, and we'll do that by putting it in parentheses. This 2 becomes Roman numeral 2, and the non-metal part, of course, we chop off the end and replace it with "ide." So this becomes iron Roman numeral 2 oxide, because the iron has a 2 plus charge. Now, the Roman numeral has nothing to do with how many things are attached. If you look up there, you see that it's 1 iron and it's 1 oxygen. The Roman numeral 2 is just for the charge. And so we look on the right-hand iron oxide over here, and we can see that the oxygen, of course, is a 2 minus, and we can uncross the charge, in this case, to get a 3 plus. And so this becomes iron Roman numeral 3 oxide. And so once again, the 3 on the iron, the Roman numeral 3, just tells you what's the charge on the iron, because iron comes in 2 flavors. It can either be 2 plus or 3 plus, either way. And so similarly, we can have, say, for copper, we can have 2 situations. Copper comes as either +1 or +2, and so it's the same situation. Sulfur is always 2 minus, and so we can use that to figure out what must the charge be on the copper. And in this first one, since we need the total to equal 0, that means the copper over here is copper 2 plus. And so this becomes copper Roman numeral 2. Sulfur becomes sulfide. And over here, since we have 2 minus, then we would have to have 2 times +1 to be on the coppers, because the total has to equal 0 for any ionic compound. And so this becomes copper Roman numeral 1. Sulfur becomes sulfide. And of course, we have things like cuprous and cupric. Don't really worry about those, as those are very old terminology. Generally, you go with the Roman numerals. Now, you don't put Roman numerals down unless you know that it has more than one possible charge. And you have silver, which is a transition element. It's always +1, so we don't say silver Roman numeral 1. We say just silver, whatever it is. And so if we had, say, this right here, even though silver is a transition element, we don't say silver Roman numeral 1. We just simply say silver chloride. And same thing with, say, cadmium. Cadmium is always +2. And so even though it is a transition element, we don't say cadmium Roman numeral 2, we just say cadmium sulfide, and we just leave it at that. But anything that is a transition element or a poor metal that does have more than one charge, such as, say, we would actually have to say, since chlorine is -1 and there's 5 of them, therefore cadmium must be +5 to equal 0, we would actually say chromium Roman numeral 5 chloride. So this is something that can trip people up. It can trip people up. When do I use Roman numerals? Most of the time, you're going to use Roman numerals if they're a transition element. Most of the time, and so the only time that you don't use it is these very few exceptions, such as silver, cadmium, and zinc. You don't use Roman numerals, and so you could have this. Well, that is just zinc chloride. Even though it's a transition element, zinc is always 2 plus. Copper is +1 +2. Iron is +2 +3. So you have to specify what you have. And so finally, we have the situation where we have these things called polyatomics, and polyatomic ions are covalently bonded with a net charge. So this would be a nitrate ion, and there's no good way of doing this nitrite without just simply memorizing them. So this is a nitrite and a nitrate. And notice that we have ites and eights. And most of your polyatomics are going to be either ites or eights. And the difference between them really is one less oxygen. So you go from NO3 to NO2, you go from 8 to an ite. And so we can have something like this, which is a phosphate, goes to a phosphite. So this is a phosphate. This is a phosphite. So you got eights and ites. And the only way you can tell the difference between them is by memorizing them. And the only pattern that you can really count on is that eights become ites. They go one less oxygen to become an 8 to an ite. And so you can have, say, sulfate versus a sulfite. And finally, if you put an H in the front, they become They become bisulfate or biphosphate. And so you can have an H, SO4 minus, and this is bisulfate. And you can also call this hydrogen sulfate. Bisulfate is an older name, but it's still very commonly used. And so hydrogen sulfate is actually the preferred newer way, but you'll see it both ways. And so you can have this right here, and this becomes biphosphate or hydrogen phosphate, either way. And it's got an 8 on the end. And so the only good way of doing this that I've found is that you just have to memorize the table. There's like 20 some odd polyatomic ions that are common, and you just have to memorize. There's no good way around it. And so naming is pretty much the same way that we've done all the other naming, in that you name what's attached, you name the metal, and then you name the polyatomic. So here we have sodium with a sulfate, and you have to memorize the table so that you don't say something like sulfur tetroxide or something like that. This is a sulfate. And so we name the metal, which is sodium, and the fact that there's two of them doesn't matter. We just name it sodium, and we say sodium, and then we just name the polyatomic. We say sulfate. It's a sodium sulfate. Definitely not a sulfur tetroxide or something like that, or disodium. We don't use the dis and tris and so forth or anything like that. So we just say sodium sulfate. And similarly, we can have another polyatomic with, say, let's see, that would be a plus. Let's say we have this right here, and we have to recognize that the NH4 is a polyatomic, and it has its own name, and that's ammonium. It's the only positively charged or cation of polyatomics. That's ammonium, and that's just the atom. So we say fluorine, that becomes fluoride. So this is ammonium fluoride. So it comes down to pattern recognition as to how to name these things when you have polyatomic ions. And so we're going to end up with, say, something like this. And of course, we need to have that in parentheses for charge balance, because remember, if we have more than one polyatomic, we have to put it in parentheses. And so this becomes, well, we name the metal calcium, and PO4 is a phosphate. So we have calcium phosphate. And so we can finally do a very good exercise, which is, we can name these things. We can say, running across the top, we can say iron 3 plus. We could say SO4 2 minus, and maybe even say a chloride. And so that would be iron Roman numeral 3, sulfate, and chloride across the top. And then we could say, we could actually pair these up. Let me move this iron down to the bottom here. And we could actually pair it up with, say, I don't know, let's go with calcium 2 plus. And you could cross these and name them. And so if we take the iron and the sulfate, we could say cross the charges. And what is this? This is iron Roman numeral 3 sulfate. And we could cross the charges on the iron and the chlorine, and we could say that looks like that. And this would also be an iron Roman numeral 3, but it's a chloride. So we have a sulfate, we have a chloride, and we can do the same thing with the calcium and the sulfate. Well, they're already equal, so we just go ahead and push them together. And that would be a calcium, name the metal, name the polyatomic. And we could have the same thing over here. We push the calcium and the chlorine together, cross the charges, and this becomes calcium chloride. And so you see there's all these different situations here. We have the iron, which has more than one charge. We have to put Roman numeral 3. And so it becomes iron Roman numeral 3, whatever it's attached to it. We have these polyatomics. We have a sulfate, which is an 8. And then we have the chlorine, which is since it's just the atom, we call it an ide. And so we push them together and make sure the charges balance out to 0. So that's how you end up naming these ionic compounds. And so that's how you do it.